Okay, we are talking about, here is our summary, our short version. Everything you need to know about the force that one charged object exerts on another. The force exerted by some charged object, Q1, on some other charged object, Q2. And what we saw from activity 5.1 was a proportion. If you have a charged object, Q1, a charged object with charge Q1, and another charged object, charge Q2, it's important that both of these charged objects are treated as point particles. In other words, their size is very small compared to the distance between them, or they're perfect spheres. And if you separate these two objects by a center-to-center distance of r and measure the force that one exerts on the other, we see the following proportion. The force that Q1 exerts on Q2 is, of course, well, let's be precise here. Let's say the magnitude of the force that object Q1 exerts on object Q2. The magnitude of that force is, of course, the same as the magnitude of the force that Q2 exerts on Q1. And these forces are proportional to the quantities of the charges multiplied by each other, the product of Q1 and Q2, proportional to that is, if you double Q1, the force doubles. If you double Q2, the force doubles. If you double both Q1 and Q2, the force increases by a factor of 4. Likewise, if you halve. But that's not the only term in the proportion. We would say that the electrical force is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So this proportion relationship is enough to compare the strength of charges, is enough to compare the strength of the forces even if you don't know what the force is, you can use the proportion to compare. For example, consider the following two situations. You've got a charge of plus Q and a charge of plus Q, and these are separated by a center-to-center distance, say d. And you've got another pair of objects. This one is plus 2Q and plus Q. And these are separated by a center-to-center distance of, say, 2d. Note that this is not to scale. Compare the forces between situation 1 and situation 2. Which interaction is a stronger force? Well, we can answer this question with the proportion relationship, because the force between these two charged objects is going to be proportional to one charge times the other charge divided by the square of the distance between them. Here's the general form of that relationship. So for these two, the force is going to be proportional to Q squared over D squared. What's that? Don't know.
Can this Velvich have 5 timers, please?
So what is this force? I don't know. But let's see if we can compare it to the force in the other situation. The same relationship says that the force here is going to be proportional to 2q times q divided by, well, let's see, the distance between them squared. What's the distance between them? 2d. Simplify, evaluate, what do you get? That would be 2q squared divided by, what do you get?
4d squared.
Good. Don't miss the opportunity to write everything down, because you are expected to mess up the easy stuff when something hard is going on. And this, of course, is equivalent to 1/2 q squared over d squared. So what's the answer to the question, which force is greater?
Number 2. No.
Oh, no. No, number 1.
Number 1.
Okay.
Known as half.
Because the force here is proportional to q squared over d squared. The force here is proportional to 1/2 q squared over d squared. So we don't know what the force is, but we know that the force in situation 1 is greater than the force in situation 2. Got it? Good. Let's carry on and talk about when we need more than a proportion. If the force, let's start with the proportion and take it beyond proportion. We would like to be able to get force in newtons and use and use our familiar units of meters for the distance between, but that means we need a unit of charge. Let's say. So before we do anything, we need to come up with a unit of electric charge. What determines the total charge on an object? And, yes, excellent. What determines the total charge on an object? As you said, the total charge will be the number of electrons plus the number of protons So one way of saying it is you're either going to have excess protons, excess electrons or missing electrons. The amount of the charge on the proton and the electron, okay, and in our language, Q is for charge. The amount of charge on an electron is equal to the amount of charge on a proton. It would be nice if we could count the extra electrons or the missing electrons and use that as a unit of charge. Let's see. By way of introduction, have you ever been sent to the store for groceries?
You can't drive.
Maybe you walked or got shoved out of the car.
Yes.
Okay.
Yes.
Would you expect your mom to shove you out of the car? Sorry for the gender stereotype. Would you expect your mom or dad to shove you out of the car and say, run into ShopRite and get me 2 eggs?
No.
No. How do you expect your to buy eggs?
Dozen.
Yeah, how many's in that cart?
Dozen.
Yeah.
12.
We find it convenient to count eggs by the dozen. dozen equals 12, and you understand if you had to buy 2 dozen eggs, you should be coming home with 24 eggs. We find this convenient because we rarely deal in single eggs. In fact, if you were a restaurant, you might buy your eggs by the gross. How many's in a gross?
144.
144, yep. If you were an ancient Babylonian, you might count your sheaves of wheat in 60s. I don't know if they had a name for that.
Bushel.
Pizzas come in 8 slices. But anyway, we have a similar way of counting electrons. Since we rarely deal in single electrons, we're going to count our electrons not by the dozen, but by the Coulomb.
By the what?
The Coulomb. C-O-U-L-O-M-B. Coulomb is abbreviated capital C. If you have a dozen eggs, you have 12 eggs. If you have 1 Coulomb of electrons,
is that a dash or is that like a negative sign?
E minus. That means
a negative charge.
Electron. These are abbreviations that are common in chemistry and beyond. That simply means an electron, P plus proton. If you have 1 Coulomb of electrons, or for that matter, 1 Coulomb, well, I'm going to get that out.
How much are in a Coulomb?
A little more. What an excellent question, Mr. G. If you have a Coulomb of electrons, you have a little more than 12. You have 6.24 times 10 to the 18th electrons.
That's a lot.
That is a whopping great number of electrons. Puppies? Mush! And that means that the charge on a single electron is equal to negative 1.6 times 10 to the negative 19th coulombs. And before you start to hyperventilate too much, what?
That'd be a positive number.
Well, by definition, we say that the charge on the electron is negative. That's a really good comment.
I just, okay.
The charge on a proton would be positive 1.6 times 10 to the negative 19th coulombs. Just like an egg equals 1/12 of a dozen eggs. Yes, 1.6 times 10 to the negative 19th of a coulomb. And don't hyperventilate. We'll go over scientific notation in a minute. And we'll talk about how to do it on your calculator. You're going to have a calculator. And everybody's favorite, I'll tell you what, let's start anew. If you are writing this down, good. If you're watching this screencast online, good. Don't worry if the screen is going by quickly, because you will be able to download and print out these notes. That's no excuse for not taking notes now. Let's sidetrack a minute to talk about a Coulomb. That is the charge on an object that has extra or missing 6.24 times 10 to the 18th electrons. And this is an absurdly large amount. In the real world, if you had an object with a charge of 1 Coulomb, and another object with a charge of 1 Coulomb. If you had these separated by a distance of about 1 meter, the force they would exert on one another is on the order of magnitude of, I think it's about on the order of 100 million tons,
That's a lot.
equivalent to 100 million tons of gravitational force. So on the order of how much force you would feel standing here with the Empire State Building on your head. So you very rarely see anything approaching a Coulomb of charge. We typically work in very small fractions of a Coulomb. We typically work in millicoulombs. 1 millicoulomb equals 1 times 10 to the negative third Coulomb, or 1 over 1,000 Coulomb. And use the prefix M.
We need to know what a millicoulomb is.
Oh, totally.
I'm going to use millicoulombs instead of normal coulombs.
We are much more likely to use millicoulombs and microcoulombs. And in fact, you're going to use milli and micro in any field of study, anything above Walmart. A micro anything is 1/1,000,000th of anything. No disrespect to our brothers and sisters who work so hard at Walmart. The prefix for microcoulomb is fun. We use a mu. Don't mess it up. Remember, draw your mu. That's what's universally used as the prefix for micro anything. Pretend like you're going to draw U, but make an ascender first. That is a lowercase mu.
Is that 1/1,000,000th of a coulomb?
That is 1/1,000,000th of a Coulomb. Okay. Millipede, 1,000 legs. Millennium, 1,000 years. Micro is a millionth. When you rub,
Thumper.
yeah, when you rub Thumper on the tube,
Who's Thumper?
you end up with about microcoulombs of charge. But it's often convenient to work in even smaller units. Anybody know the next smaller one after micro? Oh yeah, the nanocoulomb. That's 1 times 10 to the negative 9th coulombs. And I'm not even going to bother writing the fraction. Prefix for this? Sorry, no more exotic prefixes. Just a plain old lowercase n.
What if you can't do all that little M thing?
Then
Chris, it's not that hard.
you have to learn how to do it. The mu, you practice. Just come up like you're going to make a P or something and then turn it into a U. Make 10 right now. Don't make me get the lined paper. That was a good bit. The mu gave me a good payday for several years. When I worked in pharmaceuticals, they were first starting. When a drug company makes a new drug, they have to send all the data to the FDA so the FDA can decide whether it's safe and effective. And this used to be printed out and sent in a truck. One application would typically fill a tractor trailer. When they started going electronic, the first version of Microsoft Word kept changing the mu's into m's, so several applications got sent back. And this is interesting to me. but not to you. It's a good payday. Short version, pay attention to the difference between micro and milli. So, now that we have units for all the physical quantities, the unit for force of Q1 on Q2 we'll measure in old familiar newtons. The distance between two charged objects we're going to measure in good old meters. The charge on Q1 and the charge on Q2 we're going to measure in our new unit of coulombs. And we can turn our proportional representation into a quantitative representation. The amount of force that charged object 1 exerts on charged object 2 is equal to the amount of force that charged object 2 exerts on charged object 1. And that's equal to, just like before, the charge on object 1 times the charge on object 2 over the distance between them. And to make this calculation result in newtons, we include a constant to adjust the units. Just like you have a constant for converting when you go from feet to meters or from degrees Celsius to degrees Fahrenheit. This constant, yes, we are recycling lowercase k. Be alert. This is Coulomb's constant. And by definition, it is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. So this is Coulomb's law. Oh, and look, bad me. I left out the absolute value signs here.
That's confusing.
By absolute?
Yes.
Oh, so that a positive one can be attracted to a negative.
Ooh, interesting. Let's talk about the meaning of the sign next.
The meaning of what?
The meaning of plus or minus in the Coulomb expression. We have had so much fun together with pluses and minuses that now we're going to bump it up even more. The amount of force between two charged objects is equal to this quantity here. When will this quantity be greater than 0 or positive? When will this quantity be less than 0 or negative?
The distance would have to be greater for it to be well, less than 0.
Okay.
Well, no, never mind.
Wait a minute. Oh, look, thank you. I missed that square.
Yeah, never mind.
What's the physical meaning of R? Distance. Can a distance ever be physically negative? No. So the denominator here is never going to be negative. Can the top be negative?
Yes.
What has to be true for the top to be
One of the
negative?
charges negative.
Okay. One of the charges, so we could either have Q1 negative and positive Q2 or positive Q1 and negative Q2. Is there anything else that will result in a negative value for the Coulomb force?
Constant.
Oh, I know what you mean.
So physically, if this is the situation, what's physically happening?
There are more electrons than protons.
Okay. What's going to be the interaction between these two objects? And what's going to be the interaction between these two objects? The same. What will they do? Attract or repel each other?
Repel.
Attract.
Attract.
Yes. Both of these, you only get negative with opposite charges. Therefore, it's an attraction. The negative value for the Coulomb force means opposite charges are attracted. When will this Coulomb force be positive?
When both are positive.
Okay, if you have positive Q1 and positive Q2, or
Negative and negative.
or negative Q1 and negative Q2. Awesome. How do these two physically interact?
Repel.
These repel. And the other two? Also a repulsion. Excellent. So this means it's the same charge. Therefore, there's a repulsion. So, that's why we put the absolute value around this, to get the strength of the interaction. But you know that that inner quantity can tell you whether there's an attraction or repulsion. If KQ1 Q2 over R squared is less than 0, that is negative, you have an attraction. Greater than 0, repulsion. So let's stop and take a minute to consider how terribly we have abused these two symbols. When you see plus or minus, let's see if we can generate a list of what these symbols might be used to indicate. They might be used to indicate a scalar value greater than or less than 0. As in earn or spend. And that has nothing to do with their use indicating electric charge. We use the same symbols, we use the same word, but we say negative equals the charge on an electron. Completely different. What else might it be? Well, if we evaluate the Coulomb force, a plus or minus here will indicate a repulsion, or an attraction. Let's see, on a force diagram, let's say when we're adding up the total force on a force diagram like this, you might see something like this. What's the purpose of this plus or minus? Keeping track of direction on an axis. So it might also mean up or down, left or right. Plus x, minus x, like we've been doing. And there's probably some other meanings for plus and minus that I forgot to mention here. Do you want to learn the foolproof trick for memorizing which means which?
Sure.
There's no such thing, I'm sorry to say. You just gotta figure it out. And the only way to figure it out is to think of the physical meaning. You can't memorize which is which. Figure it out from the context. Think of the physics. Won't somebody think of the physics? Let's do one sample calculation, since we are recording this for posterity, and show how to work the nuts and bolts of the Coulomb expression to produce a quantitative answer in a simple problem. This is not a problem, this is the nuts and bolts of the calculation. So typically, you might, here's two charged objects, Q1 and Q2, and perhaps the charge on Q1 is positive 4 microcoulombs, and the charge on Q2 is negative 2 microcoulombs, and the distance between them 0.1 centimeter. It's a straightforward calculation to use the Coulomb expression here, but there are some pitfalls to look out for. For example, constant 9 times 10 to the 9th Newton meters squared per Coulomb squared. And you know what, guys? When we're doing this, there's no way around it for the next little while. The only thing worse than not writing all this out, sorry, I spoiled my punchline. The only thing that's more work than writing all this out in excruciating detail is not writing all this out in excruciating detail. So try to enjoy the experience of filling vast swathes of blank paper with giant calculations like this. So if we plug directly in, you will be tempted to do something like this. And this is great, but what's the problem?
They're not in the nano kilos.
Yes, totally. These quantities are not Coulombs. we need to put them in as coulombs if we expect our constant to do its work and give us newtons. So, Q1 is positive 4 microcoulombs. How many coulombs is that? Well, let's see. You know the secret. We need to turn microcoulombs into coulombs. So how many microcoulombs is in 1 coulomb?
1,000.
Yep. 1 times 10 to the 6th. So if you set it up like this, microcoulombs cancels microcoulombs, and you end up with 4 divided by 1 times 10 to the 6th, which 4 times 10 to the minus 6th coulombs. Oh yeah, we could have just said, since 1 microcoulomb equals 1 times 10 to the minus 6th coulombs, 4 microcoulombs equals 4 times 10 to the minus 6th coulombs. Now, have you heard of the Doppler effect?
Yes, I have. That's why the sirens sound like they
Oh, it's related to the Doppler effect. Is a sound, a noise will increase in frequency when it's coming at you fast.
Is it different?
The Doppler effect. Simple things are difficult when they come at you rapidly. So you have been presented with a whole bunch of things which individually are simple, but a whole bunch of them have come at you really fast.
Yes.
So the Doppler effect is going to make this seem difficult.
Yes.
So all you got to do is chill, get good notes, and practice. And that's what we're going to do next. Sorry?
You can print these on the
Yep. So let's go back and correct this calculation. If you're trying to put a number on this force, the strength of Q1 on Q2, or the force of Q1 on Q2, it's going to be, here's the K, 9 times 10 to the 9th, easy to remember. Q1 plus 4 times 10 to the negative 6th coulombs. Why write plus 4? I say just get the hang of it. In the realm of plus and minus, write yourself the plus if only to remind yourself that you checked. All of this divided by 0.01 meters squared. Reality check your units. We've got coulombs, we've got meters, and we didn't forget the blessed exponent. So now you're ready to go. Now all you need to do is to be able to drive your calculator. Because even grown-ups, well, we'll talk later about how to do this without a calculator. But while we're taking baby steps,
Is that whole part absolute value?
yes, it is. Thank you for the reminder. Oh, is this going to be an attraction or a repulsion?
Attraction.
Good. Let's say you want to type in this. You want to find the result of 9 times 10 to the 9th times plus 4 times 10 to the negative 6th times negative 2 times 10 to the negative 6th. the secret. Find the EXP or maybe EE button on your calculator. Who's got the big scary TI ones? What's that?
There's two more.
I'm doing it now.
On my little loaner ones, what does yours have, Melissa? EE or EXP?
Negative 0.072.
Nope.
It's not a
Awesome, good. But at the moment, I just want to know what kind of button you got.
button. It's not a button.
I can't find it.
Chris, you can't find it?
Double E. EE or EXP? Okay. The meaning of this, whatever button you have, this is what you type into the computer. You type 9, you press the EE button,
I don't have that.
you press 9.
Oh, I have a different button. It's times x to the n.
Nope, don't use that. Use EE or EXP.
Where's
I'll show you.
You have to look. Yes, like that. Yep, good.
Oh, where's it?
So,
About 20
let me label this. You want this.
There is. I'll show you.
You type this on your calculator. Usually you will see
It's like 9 trillion.
9 E 9.
99 is like, I don't know, a lot. 1, 2, 3.
Yeah, but never mind that.
More 9 billion.
How do we do this multiplication? Then you type times 4 EE. Next pitfall, we need 10 to the negative 6.
What is it on here? I don't have
It says error.
I'll help you find in a minute. Yes, because you fell for the next pitfall. Yes.
Chris, those trick pitfalls.
Oh, we got so many
Morse
pitfalls.
S blocking.
There's no E.
Hang on. Let's talk minus. Two minus 3 equals negative 1. This minus is a different minus than this minus. This is an operator. It means subtraction. This is, I don't know what this is called. In grown-up world, we call it a unary minus. It means it's a negative number. You got different buttons on your calculator for these.
Yeah,
Oh, I know what that
negative
one is
one's right
called.
underneath all the buttons.
It's right next to the 0.
Yes, it's the one next to the 0.
See, I knew that one.
So on your calculator, this is typed in with the unary minus button, which usually I think looks like that.
So we don't do
We do EE. 9 times 10 to the positive 9 times 4 times 10 to the
What was
negative
What was the pitfall? Oh,
6. So what did you do that made the error, Chris? You used the other minus.
no, I just didn't put the negative 6 in.
Oh, okay.
What's the other thing?
You didn't put that up there.
What's the other E?
There isn't.
Now look. Now we're ready to type in this quantity. Negative 2 times 10 to the negative 6th. That's going to come in like this. I'm going to have to cheat down here. Negative 2 times, if you have E or EXP, just think of that as times 10 to the negative 6. No, you don't. There's no 2. Oh, right. Thank you. I messed up. Remember, it's the Doppler effect. You're doing a bunch of easy things times negative 2 EE negative
What?
6. Wow, wait. Boy, we've been busy.
I feel like we did way more than.
No.
There's a couple more pages.
Oh.
So, let's go back. Just quickly review what we learned. What you're going to see, let's call this page 1. And this is the proportional form of the Coulomb equation. We use this when we are going to compare forces in two situations. You see this down here. Then we talk about, on page 2, going from that proportion to a relationship with units. So we had to make up a unit for charge. Just like we count eggs by the dozen, we count electrons by coulombs. And if you have 1 coulomb of electrons, you have 6.24 times 10 to the 18th electrons.
Can a calculator like even read that?
Nope.
Well, let's see. How would you type that into your calculator? 6.24, yep. EE 18. If you have 1 electron, how much charge do you have? You have negative, unary negative, 1.6 EE negative 19 coulombs. On this page, page 3, we talked about how much a coulomb is. 1 coulomb of charge is an absurd amount of charge. An object that actually had a charge of a coulomb on it would be very, very dangerous. More typically, we work in units of millicoulombs, MC, which is 1/1000th of a coulomb, microcoulombs with a mu, 1 times 10 to the negative 6th. This is a typical amount of charge that you might get from rubbing a balloon on your hair. Oh wait, let's see. There's about 15 coulombs of electrons in a typical lightning bolt. What? A typical lightning bolt, an average size lightning bolt, is about 15 coulombs of electrons coming from the clouds back to the ground.
So,
yes, very, very rapid.
Like all charges are coulombs?
Well, you know, if you're a restaurant, you buy your eggs by the gross. If you're a household, by the dozen. But it's all eggs. Everything electric
Is coulomb.
involves electrons going somewhere. And anytime you're counting electrons, you can count them in coulombs.
How you were saying that the Earth takes electrons and then you take them back.
Totally. So if you draw a dotted line around the whole planet Earth, the number of electrons is probably approximately equal to the number of protons. But if you've got some extras and need a place to put them, the physical Earth down here, here's again our planet entering into our day-to-day calculations again. The Earth won't notice even many thousands of coulombs coming or going. Yes, it's crazy. Let's see, next page. So, because even a coulomb of charge on, if you had a coulomb of charge on this bowling ball, which would be an absurdly strong charge, you could never keep it there in the real world. but that would still be only a tiny, tiny proportion of the number of protons in this polygon. Many millionths. And don't get sidetracked, Chris. Hang on. So let's see. We have prefixes on page 3. Page 4, we introduced the quantitative form of the Coulomb's law equation. And Coulomb's constant, which gives us newtons, provided we put in coulombs and meters. Here on page 5, we talked about the sign of the Coulomb force. A negative result means that we have opposite charges, a plus and a minus, or a minus and a plus. So that means an attraction, same charge, positive. Wow, have I been talking that long? That's amazing.
Yeah.
I'm so sorry. Well, at least, although you didn't get the class time to practice, at least now we have this reference we can go to on the website forever. And on page 6, we talked about, all the different meanings of positive and negative, of plus and minus. And how, if you find yourself doing a simple electrostatics problem and getting a headache because of all the different pluses and minuses, yes, that's right, you're doing it correct. On page 7, we talked about how to actually get this into your calculator and get out a result that makes sense. So we are going to end the screencast there. Be very proud of yourself. All of these things are in the electrostatics packet as well, but here they are in one place. End of thing. Sure hope we caught that. Assignment.